Okay, so here's a theorem. And so this is all these theorems are very useful for us. This is why we're going to prove them. We'll do some examples here in a minute. You'll see these in action. But for now, so let's let x be, guess what? A discrete random variable. And C1, C2, etc., up to Cn are real constants. And let's let G1, G2, etc., up to Gn, let's let these guys be functions. These are functions. Then, guess what? It turns out that if I want to, let's say I want to take a, if I want to take this random variable x, apply this function to it, and multiply by C1, and then, take C2 times G2 of x plus ... Cn times Gn of x. This expected value I can actually write as the sum of the ck times the expected value of gk of x. Okay. Now this looks really complicated and stupid, but it's not. It's really great. It means that I can find the average of this. I can find the average of the function of the kth function of x, and multiply it by this weight. You can think of this as another weight over here, and then sum up over all values of k. So let's prove it. I promise. We'll use this someday. So first of all, I'm going to start with the left-hand side and try to get to the right. So this is my left-hand side, LHS. So the LHS is, let's see, can I write that more succinctly? Yeah, I think I can. I think I can write that as the expected value of the sum C sub k, G sub k of x, right? Let's see. I've got k down here. What should I use for a dummy index? Maybe we'll use the Greek letter xi. It's not used nearly enough. Whoops, not yet, though. I'm getting ahead of myself here. Over k. There we go. Yeah, I'm going to go k goes from 1 to n. All right, good. Yeah, do you agree? This is the same as all of this. Okay, just using summation notation. All right, now, whenever you go about trying to prove something, if you don't know where else to start, probably the best place to go is the definition. So let's apply the definition of expected value. The definition of the expected value functional there. What's the definition tell us to do? It says to sum up all of the things that look like this, but weighted against this probability function. Okay, so I'm going to put all those things. I'll put them right here. Okay, k equals 1 to n ck gk of. Now I need a dummy variable, right? So I'm summing up all the possible values of x. So I'm going to sum up over that dummy variable, and I'll use the Greek letter xi. You could use whatever you like. Okay, I just like it because it looks cool, and against the chance that x equals xi. Okay. All right. So now, what could we do here? What could we do with this? Well, I'll tell you what. One thing I think we could do is maybe note that these parentheses really aren't necessary, right? I can sort of dissolve them, and in fact, when I do that, what happens is this probability part comes inside the summation, doesn't it? Okay, so, and that's perfectly fine because we're just distributing it out over this sum in here. Okay. Now what I'm going to do is I'm going to change the order of the summation symbols, and that's perfectly okay because it doesn't matter what order you add things up in, right? Okay. Sometimes you want to be careful of your summation indices and adjust for that, but we're okay there. Okay. So I think I can rewrite this as the sum, k goes from 1 to n, of the sum k of over this c values of the c sub k, g sub k of c times the probability that x equals c. Now let's see, what can I do here? Guess what? This does not depend on k, so I can pull it out, right? Anything that doesn't depend on, it doesn't depend on c. Anything that does not depend on c, I can pull out of that inside summation, right? This is the only thing that doesn't. These two things have c's in them, right? So actually, I think we're done. We're basically there because all this stuff now is the same as the sum from k goes from 1 to n times c sub k times the sum over the c values of g sub k of c times the chance that x equals c. But guess what? Come on, guess. Guess what? Guess what? This, what is this? This is just the expected value of g sub k of x. Okay, isn't it? See, it's the sum. It's a weighted average of these guys. Okay, so we're there. We're done. Proved. Finally, last but not least, finally, and this, I know all this is probably hurting your head, but that's okay. It's supposed to. This is a real useful little theorem. Okay, let x be a discrete. Let x be discrete random variable with mean expected value of x is mu. Okay. By the way, sometimes if it's fairly obvious that we mean the expected value of x, we may or may not include the brackets there. Okay. So the expected value or the mean is mu. Then it turns out the variance of x can be written this way. Okay. Now, I don't know what this is called, but I call it the inside-outside formula. When I was a little kid, I had a book called Inside, Outside, Upside Down. Inside, outside. Inside, outside. Inside, outside. Get it? The exponent, the 2, is inside the brackets. Here it's outside the brackets. Okay. So this is the expected value of the square of the random variable. This is the square of the expected value. In general, they are not the same. If you can remember that, inside minus outside, then you're golden. Okay. Let's see if we can prove this. So I'm going to start with the definition of the variance of x. By the way, now would be a good time for you to pause the video and try to do this on your own. But if you don't want to, you just watch me do it. I'm going to start with, guess what? I don't know what else to do, but I'm going to try the definition of variance. Definition of variance. Definition of variance. It says to take the expected value of x minus the average of it squared, right? Okay. So I'll tell you what, I'm just going to do what I know how to do. I can square that stuff on the inside, right? Okay. And now, what is that stuff on the inside? And remember, these x's are functions, and these mu's are constants. It's perfectly okay to multiply this stuff like they were just numbers, right? Sort of. And it's just x squared minus mu x plus mu squared. Yeah, of course it is. So this is the expected value of x squared minus 2 mu x plus mu squared, isn't it? Now, I'm going to apply a theorem. by this theorem, the expected value of the sum of a bunch of stuff is the sum of the expected values, right? So this is just the expected value of x squared minus the expected value, or maybe I should keep it like this, plus the expected value of negative 2 mu x, and then plus the expected value of mu squared. Okay? Right? Now, expected value of x squared, that's like that. Now, remember we also know that we can pull constants out of the expected values, right? Because remember, the expected value is really a summation, isn't it? It's really, yeah, remember that? It's really a summation. You can think of it like that if you look at the definition. Okay, so I can pull out that negative 2 mu, and then it's like that, isn't it? Okay, now finally, what's the expected value of mu squared? Mu squared is a constant. Expected value of a constant is a constant. Duh. Okay, so this is the expected value of x squared minus 2 mu. Hey, this is the expected value of mu is also mu. This is mu. Mu squared. Hey, a mu squared minus 2 mu squared is minus a mu squared. And we're done. Okay? Whew. Let's do some examples.